For decades, we believed the laws of physics were complete. But deep beneath the French-Swiss border, scientists are discovering signs that something doesn't add up. Inside, CERN particles behave slightly wrong, bending magnetism, refusing to follow the equations we trust. These are not mistakes, they are cracks. And if the laws of physics can crack, then the universe you live in may be far less stable than it appears. To understand why we need to go back to the beginning, and don't forget, subscribe to our channel. Every proton collision in the LHC recreates a specific moment in cosmic history. Not the Big Bang itself, but 1/1,000,000th of a second afterward, when the universe had already cooled enough for quarks to exist, but not yet cool enough for protons to form. At 5.5 trillion degrees Celsius, matter as we know it can't exist. Atoms would instantly vaporize. Nuclei would disintegrate. What you have instead is quark-gluon plasma, a state of matter that hasn't existed naturally in our universe for 13.8 billion years. Understanding this requires precision about what actually happens in that collision point. The kinetic energy of two protons, each moving at essentially light speed, converts directly into mass through Einstein's equation running in reverse. Energy becomes particles, but not randomly. The conversion follows specific rules dictated by quantum field theory and conservation laws. For every particle of matter created, an antiparticle appears. Quarks and antiquarks, electrons and positrons, muons and antimuons, always in pairs. These particle pairs exist in a seething, chaotic soup for approximately 10 to the minus 23 seconds. During this time, they're not bound into stable structures. Quarks swim freely, something impossible under normal conditions, because the strong nuclear force increases with distance. Try to separate quarks and the force grows stronger, eventually creating new quark-antiquark pairs, rather than allowing isolation. This property, called confinement, makes individual quarks unobservable in nature. But in quark-gluon plasma, at temperatures exceeding 2 trillion Kelvin, the thermal energy overwhelms confinement temporarily. Then the plasma cools. As the energy dissipates into an expanding volume, quarks begin binding together in triplets. 3 quarks form a proton. 3 different quarks form a neutron. The strong force crystallizes from its high-temperature symmetric phase into the confining force we observe today. This phase transition from deconfined quarks to confined hadrons occurred universe-wide at roughly 1 microsecond after the Big Bang. What makes the LHC invaluable is its ability to study this transition in controlled conditions. By varying collision energies and analyzing the debris patterns, physicists map how the strong force behaves at different temperatures. They've discovered that quark-gluon plasma flows almost like a perfect fluid, with virtually zero viscosity, contradicting earlier predictions that it would behave like a gas. This finding has implications for understanding the early universe's evolution, and possibly for neutron star interiors where similar conditions might exist. But the LHC's primary achievement remains the Higgs boson discovery. The theoretical framework predicting the Higgs dates to 1964, when Peter Higgs, Francois Englert, and Robert Brout independently proposed a mechanism to explain why fundamental particles have mass. The problem they addressed was profound. According to quantum field theory's symmetry principles, fundamental particles should be massless. Yet, electrons have mass, quarks have mass. W and Z bosons, carriers of the weak nuclear force, have substantial mass. Their solution involved proposing an additional quantum field permeating all space with a non-zero value, even in vacuum. Particles acquire mass by interacting with this field. The stronger the interaction, the greater the mass. Photons don't interact with the Higgs field at all, which is why they're massless and travel at light speed. Electrons interact weakly, giving them relatively small mass. Top quarks interact very strongly, making them nearly as heavy as entire gold atoms, despite being fundamental point particles. The Higgs boson is the quantum excitation of this field, the particle that appears when you pump enough energy into the Higgs field to create a ripple. But it's extraordinarily unstable, decaying in roughly 10 to the minus 22 seconds through several possible channels. It might decay into bottom quark, antiquark pairs, into W boson pairs, into tau lepton pairs, into photon pairs, or into Z boson pairs. Each decay mode occurs with a probability calculable from standard model parameters. Finding the Higgs required analyzing trillions of collisions to identify a tiny excess of events at 125 giga-electron volts. At this energy, slightly more photon pairs and lepton combinations appeared than random background processes would produce. This excess was statistically significant 5 sigma, meaning the probability of it being a random fluctuation was less than 1 in 3 million. When both ATLAS and CMS detectors independently confirmed the same signal, the discovery was certain. But measuring the Higgs mass opened new questions. At 125 GeV, the Higgs is lighter than many theoretical models predicted, but heavier than others. More concerning, this particular mass value creates what's called the metastability problem. When you calculate the effective potential energy of the Higgs field across all possible field values, accounting for quantum corrections from virtual particles, you find that our current vacuum state, where the Higgs field sits at about 246. GeV isn't the absolute minimum energy configuration. There exists a deeper minimum at much higher field values. Our vacuum is like a ball resting in a shallow valley on a hillside, with the true valley bottom much further down the slope. Quantum mechanics allows the ball to tunnel through the hill rather than rolling over it, transitioning from our metastable vacuum to the true stable vacuum. If this transition occurs, a bubble of true vacuum would nucleate somewhere in space and expand at light speed, with the bubble wall converting everything it touches into matter governed by different physics. Atoms couldn't exist in the new vacuum. Stars would extinguish. Everything would end, though, when is calculable. The probability is so low that it likely won't happen for 10 to the 100th years, vastly exceeding the current age of the universe. The LHC has also revealed how matter behaves at energy densities approaching the Planck scale, where quantum gravity effects might emerge. By colliding, heavy ions lead nuclei containing 208 nucleons. Physicists create conditions of extreme density and temperature, probing the boundaries where our understanding of space-time itself becomes uncertain. These collisions don't produce individual particle interactions, but rather collective effects involving hundreds of quarks and gluons simultaneously. One remarkable discovery from these heavy ion collisions involves elliptic flow patterns. When two lead nuclei collide off-center, they create an almond-shaped region of quark-gluon plasma. This asymmetric shape generates pressure gradients that cause particles to be ejected preferentially along certain axes. Measuring these flow patterns reveals the plasma's viscosity, its equation of state, and how quickly it thermalizes. The data shows thermalization occurs in less than 1 femtometer. C, meaning the plasma reaches thermal equilibrium faster than light crosses a proton's diameter. Additionally, the LHC has confirmed quantum entanglement at unprecedented energy scales. In 2022, physicists detected entanglement between top quarks, the heaviest known fundamental particles. Top quarks decay in roughly 5 times, 10 to the minus 25 seconds, yet their spin correlations showed clear signatures of quantum entanglement. This demonstrates that quantum mechanical non-locality persists even in the violent high-energy environment of particle collisions, suggesting entanglement is robust under extreme conditions that approximate the early universe. These findings aren't merely confirming what theorists expected. They're providing quantitative data that constrains speculative physics proposals. For instance, certain supersymmetry models predicted different Higgs masses, different decay branching ratios, different production cross-sections. The measured values rule out large regions of parameter space, eliminating entire classes of beyond standard model theories. Similarly, searches for supersymmetric partner particles have set mass limits exceeding several TeV, forcing theorists to revise their models or propose why superpartners might be heavier than originally anticipated. But the most intriguing aspect of LHC physics is what it reveals about the universe's initial conditions. The quark-gluon plasma properties constrain models of the QCD phase transition in the early universe, affecting predictions about primordial nucleosynthesis, the formation of light elements in the first few minutes after the Big Bang. The Higgs properties determine the universe's stability history, potentially explaining why the electroweak phase transition occurred at the temperature it did. And The absence of certain predicted particles, magnetic monopoles, for instance, tells us something about grand unification theories and cosmic inflation. Still, the largest mystery remains untouched: the composition of the invisible universe. Dark matter constitutes 27% of the universe's mass energy, dark energy, another 68%. Neither has been detected at CERN despite extensive searches, which raises the question: are we looking in the wrong place with the wrong tools for the wrong signatures? Or is the dark sector fundamentally disconnected from standard model physics, except through gravity, the visible universe? Everything we can see, touch, measure directly with electromagnetic radiation represents 5% of reality. This isn't philosophical speculation or theoretical extrapolation. It's empirical fact derived from gravitational measurements, cosmic microwave background analysis, and large-scale structure surveys. 27% of the universe is dark matter, 68% is dark energy, and both are completely absent from the standard model. Dark matter's existence was first inferred in the 1930s, when Fritz Zwicky measured the velocities of galaxies in the Coma cluster. He found they were moving far too fast. The visible matter's gravity was insufficient to hold the cluster together. The galaxies should have been flung apart billions of years ago, yet they remained gravitationally bound. Zwicky concluded there must be Dunkel materia dark matter providing additional gravity. For decades, astronomers hoped dark matter would turn out to be ordinary matter that simply didn't emit light. Perhaps vast numbers of brown dwarfs, black holes, or rogue planets lurked in galactic halos. These were called MACOs, massive compact halo objects. But microlensing surveys in the 1990s ruled this out. When a massive object passes in front of a distant star, its gravity bends, the starlight temporarily brightening the star. By monitoring millions of stars, astronomers could detect MACOs and measure their abundance. The results were definitive. MACOs can't account for more than a small fraction of dark matter. This means dark matter must be something genuinely exotic. The leading hypothesis is WIMPs, weakly interacting massive particles. These would be particles perhaps 10 to 1,000 times heavier than protons, interacting only through gravity and possibly the weak nuclear force, completely transparent to electromagnetism and the strong force. They would pass through ordinary matter almost without interaction, occasionally scattering off atomic nuclei through weak force exchange. CERN has been searching for WIMPs in multiple ways. Direct production searches look for collision events, where particles appear to be missing. Conservation of momentum would be violated unless something invisible carried away energy. Indirect searches look for excess antimatter in cosmic rays, which might be produced when dark matter particles annihilate in the galactic halo. Neither approach has yielded confirmed detections, though several anomalous signals have appeared and disappeared as statistics improved. The null results are scientifically valuable because they constrain WIMP properties. If WIMPs exist and have masses below approximately 1 TeV, their interaction cross-section must be smaller than certain values, otherwise the LHC would have produced them. These constraints eliminate many supersymmetry models, which predict supersymmetric particles in the 100 GeV to few TeV range, serving as WIMP candidates. But dark matter might not be WIMPs at all. Alternative candidates include axions, extremely light particles with masses perhaps a billionth of an electron volt, originally proposed to solve the strong CP problem in quantum chromodynamics. Axions would be produced copiously in stellar cores and the early universe, and while each individual axion has negligible mass, their vast numbers might account for dark matter. Detection requires different experimental approaches. Resonant cavity experiments, searching for axion to photon conversion in strong magnetic fields. Another possibility is primordial black holes formed in the first second after the Big Bang from density fluctuations. Unlike stellar mass black holes created by dying stars, primordial black holes could have any mass from microscopic to thousands of solar masses. Recent gravitational wave detections of black hole mergers in the tens of solar masses range have renewed interest in this idea, though most cosmologists consider it unlikely that primordial black holes constitute the majority of dark matter. The dark matter mystery deepens when you consider its distribution. Galaxies sit inside massive dark matter halos, extending far beyond visible matter. These halos have specific density profiles. The density decreases with distance from the galactic center, but more slowly than visible matter density. The Milky Way's dark matter halo probably contains hundreds of billions of solar masses, while visible matter stars, gas, dust totals only about 60 billion solar masses. Gravitational lensing provides the most direct evidence for dark matter's distribution. When light from distant galaxies passes near massive clusters, the cluster's gravity bends the light paths, distorting background galaxies into arcs and rings. By mapping these distortions across the sky, astronomers reconstruct the mass distribution of galaxy clusters. Invariably, the mass far exceeds what visible matter can account for. The Bullet cluster provides a particularly striking example. Two galaxy clusters collided, and the hot gas visible in X-rays separated from the dark matter, visible only through gravitational lensing. This spatial separation demonstrates that dark matter can't be simply modified gravity, because different components of the system experience different gravitational effects. Yet dark matter represents only 27% of the cosmic mystery. Dark energy, 68%, is even more perplexing because it doesn't behave like matter at all. The discovery came from Type Ia supernovae observations in the late 1990s. These supernovae occur when white dwarfs accrete matter from companion stars until reaching the Chandrasekhar limit 1.4 solar masses, at which point they explode with remarkably consistent brightness. This makes them standard candles for measuring cosmic distances. By comparing apparent brightness to intrinsic luminosity, astronomers calculate distances to supernova host galaxies. Two independent teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, measured dozens of distant supernovae and found something unexpected. The supernovae were dimmer than predicted, meaning they were farther away than expected if the universe were decelerating. The only explanation, the universe's expansion, is accelerating. Something is pushing space apart with increasing strength over time. This something is dark energy. The simplest interpretation is Einstein's cosmological constant, a constant energy density filling space uniformly. As the universe expands, more space gets created, and since energy density remains constant, total dark energy increases. This drives accelerating expansion through a sort of gravitational repulsion. But there's a monumental theoretical problem. When physicists calculate what the vacuum energy should be, based on quantum field theory, summing contributions from all virtual particles fluctuating in and out of existence, they get a number roughly 10 to the 120th power, larger than the observed cosmological constant. This is the worst prediction in physics history, off by 120 orders of magnitude. Various solutions have been proposed. Perhaps the vacuum energy contributions from different fields precisely cancel through some unknown symmetry, leaving only a tiny residual. Perhaps our universe is one of many in a multiverse, and we observe a small cosmological constant, because only universes with small values allow structure formation, and thus observers. Perhaps dark energy isn't constant, but a dynamical field called quintessence that evolves over time. CERN can't directly probe dark energy because it operates at particle physics scales, while dark energy manifests cosmologically. However, certain theoretical frameworks connect the two. If the Higgs field couples to a quintessence field collider, experiments might detect subtle modifications to Higgs properties. If dark energy arises from extra dimensions, those dimensions might produce detectable signatures in high-energy collisions. More speculatively, some physicists propose dark matter and dark energy might be related through a dark sector, a complete parallel set of particles and forces that interact with standard model particles only gravitationally and possibly through Higgs portal interactions. In this picture, dark matter would be dark sector matter. Dark energy would arise from dark sector fields, and rare processes involving the Higgs boson might provide the only experimental window into this hidden universe. The frustration for experimentalists is palpable. We know with certainty that 95% of the universe consists of things the standard model doesn't describe. We can measure dark matter's gravitational effects with precision rotation, curves, lensing, distortions, cosmic microwave background, anisotropies, all yield consistent values for dark matter density. We can measure dark energy's equation of state through supernova distances, baryon acoustic oscillations, and large-scale structure growth. Yet we cannot identify what these things actually are. This situation is historically unprecedented. In previous physics revolutions, experimental anomalies preceded theoretical understanding. Observations of atomic spectra led to quantum mechanics. Observations of Mercury's orbit led to general relativity. But with dark matter and dark energy, we have enormous quantities of something whose fundamental nature remains completely mysterious despite decades of intensive research. CERN's searches continue because even null results constrain theoretical possibilities. Every energy range explored without WIMP detection narrows parameter space. Every Higgs portal search that comes up empty eliminates certain dark sector models. The process is slow and methodical, ruling out possibilities systematically rather than making dramatic discoveries. But beyond dark matter and dark energy lies an even deeper mystery, one that threatens the very existence of everything. Because the universe, according to calculations based on the measured Higgs mass, shouldn't exist at all. The Big Bang should have produced exactly equal amounts of matter and antimatter. This isn't theoretical speculation, it's a direct consequence of fundamental symmetries in particle physics. When energy converts to mass, it creates particle-antiparticle pairs. An electron appears alongside a positron. A quark appears alongside an antiquark. Every process in quantum field theory conserves baryon number, lepton number, and numerous other quantum charges, which means matter and antimatter must be created symmetrically. When matter meets antimatter, they annihilate with perfect efficiency, converting their entire rest mass into energy, according to Einstein's equation. An electron colliding with a positron produces 2 gamma-ray photons, carrying 511 kilo-electron volts each. The electron's rest mass energy. A proton annihilating with an antiproton releases nearly 2 billion electron volts in a cascade of pions and other mesons that quickly decay to photons, neutrinos, and electrons. Given these facts, the universe should contain only photons. In the first microsecond after the Big Bang, temperatures exceeded 10 trillion Kelvin, hot enough for photons to spontaneously create matter-antimatter pairs, which would immediately annihilate back to photons in a continuous cycle. As the universe cooled and expansion lowered the photon energies below the threshold for pair production, all matter and antimatter should have found their counterparts and annihilated, leaving a universe filled with cooling, radiation, and nothing else. Yet every atom in your body is matter, not antimatter. Every star is matter. Every planet, every galaxy, every structure we observe across 13.8 billion light-years consists of matter. Antimatter appears only transiently created in high-energy collisions, or radioactive decays, existing briefly before encountering matter and annihilating. The asymmetry is quantified precisely through cosmological observations. The cosmic microwave background, the relic radiation from 380,000 years after the Big Bang, shows a perfectly smooth blackbody spectrum characteristic of pure photon radiation with minimal baryon contamination. By measuring the temperature fluctuations and computing the photon-to-baryon ratio, cosmologists determined that for every 10 billion matter-antimatter pairs that annihilated, approximately 1 extra matter particle survived. That 1 in 10 billion excess comprises everything that exists. This asymmetry requires 3 specific conditions, first articulated by Andrei Sakharov in 1967. First, there must be processes that violate baryon number conservation, allowing the total number of matter particles to change. Second, these processes must violate C, symmetry, charge, conjugation, and CP, symmetry combined, charge and parity, meaning they treat matter and antimatter differently. Third, these processes must occur out of thermal equilibrium, preventing the asymmetry from being washed out by rapid forward and backward reactions. The standard model satisfies all 3 conditions, but insufficiently. CP violation has been observed in the weak interactions of kaons and B mesons particles, containing strange and bottom quarks. These particles decay slightly differently from their antiparticles, demonstrating that nature doesn't treat matter and antimatter identically. The discoverers of CP violation in kaons, James Cronin and Val Fitch, received the Nobel Prize in 1980, and the discovery in B mesons earned another Nobel in 2008. However, the CP violation observed in these systems is too weak by approximately 10 orders of magnitude. If you calculate how much matter-antimatter asymmetry the standard model's CP violation can generate in the early universe, you get a number far smaller than the observed 1 in 10 billion excess. Something beyond the standard model must be generating additional CP violation. CERN experiments are searching for this additional source through precision measurements of particle decays. The LHCb detector specializes in studying B quarks and their antimatter counterparts, measuring decay rates and angular distributions with extreme accuracy. Any deviation from standard model predictions could indicate new particles or forces contributing to CP violation. One particularly intriguing set of measurements involves B meson decays to kaons and leptons. The standard model predicts these decays should occur with specific branching ratios and angular distributions. Recent LHCb data shows potential deviations. Certain decay modes appear slightly more or less common than predicted, and the angular distributions of final state particles don't quite match theoretical expectations. The statistical significance isn't yet sufficient to claim discovery, but if confirmed with more data, this could be evidence for leptoquarks hypothetical particles that couple to both quarks and leptons, potentially mediating new interactions that contribute to CP violation. Another approach examines antimatter directly. CERN's antimatter factory produces antiprotons by smashing protons into a metal target, then slows them using electromagnetic fields and combines them with positrons to create antihydrogen atoms. These antihydrogen atoms are trapped using magnetic bottles, specially configured fields that confine the electrically neutral but magnetically polarizable antimatter atoms without letting them touch the container walls and annihilate. Once trapped, physicists can perform spectroscopy on antihydrogen, measuring how it absorbs and emits light. If matter and antimatter are truly symmetric under CPT symmetry, the combined operation of charge, conjugation, parity, inversion, and time reversal, then antihydrogen should have exactly the same spectral lines as hydrogen. Any difference would indicate CPT violation, which would be revolutionary. Because CPT symmetry is a fundamental theorem in quantum field theory, essentially required for mathematical consistency. So far, measurements show perfect agreement. Antihydrogen's 1s/2s transition frequency matches hydrogen's to within 2 parts in 10 trillion, limited by experimental precision rather than any detected difference. Antihydrogen falls downward in Earth's gravitational field, just like ordinary hydrogen, ruling out exotic anti-gravity proposals. Every measurable property appears identical to normal matter except for the sign of the electric charge. This creates a puzzle. If matter and antimatter are truly symmetric in all measurable properties, why does the universe contain only one and not the other? The asymmetry must have been generated dynamically in the early universe through processes we don't yet understand. One possibility involves leptogenesis, a theoretical mechanism where very heavy particles, called right-handed neutrinos, existed in the early universe. These particles would have masses perhaps 10 trillion times heavier than protons, accessible only at energies far beyond any collider's reach. When right-handed neutrinos decay, they could produce an excess of leptons over antileptons through CP violating decays. This lepton asymmetry would then convert to a baryon asymmetry through Sphaleron processes, quantum tunneling events involving the weak force that change lepton number and baryon number while preserving their difference. The LHC can't directly test leptogenesis because the right-handed neutrinos are too heavy to produce, but it can test predictions of theories that include leptogenesis. Many such theories also predict light sterile neutrinos, additional Higgs bosons, or other particles within the LHC's energy reach. Finding these would provide indirect evidence supporting the leptogenesis framework. Alternatively, the asymmetry might have been generated during the electro-weak phase transition when the Higgs field acquired its non-zero vacuum value. If this transition was first order, meaning it proceeded through bubble nucleation rather than a smooth crossover, then CP violating interactions at the bubble walls could generate baryon asymmetry as the bubbles expanded through space. This scenario, called electroweak baryogenesis, requires additional sources of CP violation beyond the standard model, but within the energy range accessible to colliders. Measurements of the Higgs boson's properties constrain electroweak baryogenesis significantly. The Higgs self, coupling how strongly the Higgs field interacts with itself, determines whether the electroweak phase transition was first order or smooth. Current data suggests it was a smooth crossover, which would rule out standard electroweak baryogenesis scenarios. However, if there are additional Higgs bosons, or if the Higgs sector is more complicated than the minimal standard model version, a first-order transition might still be possible. Beyond matter-antimatter asymmetry, CERN has revealed another impossibility. Quantum entanglement persists in environments where classical intuition suggests it should be destroyed. Quantum entanglement occurs when two particles are created together or interact in ways that correlate their quantum states. If you measure one particle's spin pointing up, the other spin must point down regardless of the distance separating them. This correlation is instantaneous and has been verified in experiments across kilometers of separation. Einstein famously called it spukhafte Fernwirkung, spooky action at a distance, and considered it evidence that quantum mechanics was incomplete. But Bell's theorem and subsequent experiments proved Einstein wrong. The correlations are real, not due to hidden variables or prior agreement between particles. When you measure one entangled particle, you genuinely affect its partner instantaneously, though without transmitting information faster than light because the measurement outcomes are random. In 2022, the ATLAS collaboration detected entanglement between top quarks produced in proton collisions. Top quarks are remarkable particles. They're the heaviest elementary particles known, weighing about 173 giga-electron-volts, roughly as much as an entire atom of tungsten. They're also the most unstable, decaying in approximately 5 times 10 to the minus 25 seconds, through weak interactions that convert them to bottom quarks and W bosons. Despite this infinitesimal lifetime and the violent environment of their creation, particle collisions at 13 tera-electron-volts generating temperatures of several trillion. Kelvin-top quark pairs produced in proton collisions show quantum entanglement in their spin states. The ATLAS team measured this by analyzing the angular distributions of particles produced when top quarks decay. The correlations matched quantum mechanical predictions for entangled states rather than classical correlations from independently decaying particles. This finding is theoretically profound because it demonstrates that quantum coherence survives in extreme conditions approaching those of the early universe. Decoherence, the process by which quantum superpositions collapse into definite classical states, occurs when systems interact with their environment. In the chaotic environment of a particle collision, with hundreds of particles being created and annihilated, you'd expect decoherence to happen essentially instantaneously. Yet entanglement persists long enough to be imprinted on the decay products. This has implications for understanding the quantum to classical transition in cosmology. In the first instance after the Big Bang, the universe was a quantum system, a superposition of all possible field configurations. As it expanded and cooled, it underwent decoherence, transitioning into the classical universe we observe. But exactly when and how this occurred remains unclear. The observation of entanglement at LHC energies suggests quantum effects were robust in the early universe, potentially affecting structure formation, baryogenesis, and other primordial processes. CERN experiments have also discovered exotic hadrons that challenge our understanding of the strong force. The standard model predicts that quarks combine in specific ways. Mesons contain one quark and one antiquark, while baryons contain 3 quarks. This pattern arises from the mathematics of quantum chromodynamics, QCD, the theory of the strong force. Quarks carry color charge, analogous to electric charge, but with 3 types called red, green, and blue. Physical particles must be color neutral, which is achieved by combining 3 quarks of different colors, baryons, or a quark-antiquark pair, where the antiquark carries the anticolor mesons. Yet, in 2015, the LHCb collaboration announced the discovery of pentaquarks particles, containing 4 quarks and 1 antiquark. The signature appeared in the decay of lambda B baryons, where an intermediate state containing 5 quarks briefly existed before decaying to other particles. Subsequent measurements confirmed multiple pentaquark states with different masses and decay properties. Pentaquarks aren't forbidden by QCD, but their existence wasn't anticipated by most theorists. The question is whether they're tightly bound 5-quark objects or loosely bound molecular states where a baryon and a meson stick together through residual strong force. Current data suggests they're likely molecular states, analogous to how protons and neutrons bind through residual strong force to form atomic nuclei. But their mere existence proves that quark combinations are more diverse than the simple quark model suggested. Similarly, tetraquarks, 4 quark states containing 2 quarks and 2 antiquarks, have been discovered at CERN and other facilities. Some tetraquarks appear to be compact objects, where all 4 quarks are tightly bound. Others are clearly molecular states. Distinguishing between these scenarios requires precision measurements of masses, decay widths, and production mechanisms which ongoing LHC experiments are providing. These exotic hadrons are forcing theorists to refine their understanding of confinement, the property of QCD that prevents quarks from existing individually. We know confinement occurs because isolated quarks have never been observed, only combinations that are color neutral. But the detailed mechanism, how the strong force increases with distance to prevent separation, remains incompletely understood, and exotic hadrons provide crucial data for testing theoretical models. All these findings, the matter, antimatter, asymmetry, quantum entanglement at high energies, exotic hadrons, point to the same conclusion: the universe is more complex than the standard model describes, operating through mechanisms we're only beginning to glimpse. And lurking behind these mysteries is a threat to existence itself. When physicists measured the Higgs boson's mass at 125 giga-electron volts and calculated its implications for vacuum stability, the result was unsettling. Our universe exists in what's called a metastable vacuum state, not the absolute lowest energy configuration possible, but a local minimum that could theoretically transition to a deeper minimum through quantum tunneling. Understanding this requires examining how potential energy varies with field values. The Higgs field has a potential energy function that depends on its value at each point in space. At high temperatures immediately after the Big Bang, thermal energy kept the Higgs field at 0, and the potential energy function had its minimum at 0. As the universe cooled, the shape of the potential energy function changed due to quantum corrections, developing a Mexican hat shape with a valley surrounding a central peak. The Higgs field then rolled down from the unstable peak to the stable valley through a process called spontaneous symmetry breaking. It settled at a value of approximately 246 giga-electron volts, which is the vacuum expectation value we observe today. This non-zero vacuum value is what gives particles their masses through their interactions with the Higgs field. However, quantum corrections from virtual particles, top quarks in particular, due to their large mass and strong coupling to the Higgs, modify the effective potential at very large field values. When theorists calculate these corrections using the measured Higgs mass, top quark mass, and strong force coupling constant, they find that at field values around 10 to the 10th giga-electron volts, the potential energy becomes lower than it is at our current vacuum value of 246 GeV. This creates a problem. Our vacuum is not the true ground state. It's a false vacuum, separated from the true vacuum by an energy barrier. Quantum field theory allows systems to tunnel through energy barriers, even when they lack the classical energy to go over them. This is quantum tunneling, the same effect that allows alpha particles to escape atomic nuclei in radioactive Acontely decay. If the Higgs field tunnels from our current value to the higher value, where the potential is deeper, a bubble of true vacuum would nucleate and expand at the speed of light. Inside the bubble, the Higgs field would have a different value, meaning all particle masses would change. Electrons might become heavier, quarks lighter, or vice versa, depending on the exact field value. Atoms, as we know them, couldn't exist. Chemistry would be different or impossible. The bubble wall would convert everything it touches into matter governed by completely different physical laws. The crucial question is, how likely is this to happen? Quantum tunneling rates depend exponentially on the height and width of the energy barrier. A high, wide barrier makes tunneling extraordinarily improbable. Calculating the tunneling rate requires sophisticated quantum field theory techniques, including evaluating what's called the bounce solution, a configuration of the field that represents the optimal tunneling path. The results published by several independent groups suggest the vacuum decay rate is incredibly low. The probability per unit volume per unit time is roughly 10 to the minus 100 per cubic centimeter per second. Integrated over the entire observable universe and its current age, the total probability that vacuum decay has occurred somewhere is negligible, far less than 1 in 10 to the 50th. Extending this to the future vacuum, decay is unlikely to occur within 10 to the 100 years, a timescale so vast that it exceeds the time for black holes to evaporate through Hawking radiation, for protons to decay, if they do for the prados, last stars to extinguish. So, in practical terms, vacuum instability is not a threat. The universe will expand, cool, and eventually reach heat death, long before vacuum decay becomes likely. But the theoretical implications are profound. Some physicists interpret metastability as evidence for the multiverse. In eternal inflation scenarios, quantum fluctuations during the inflationary epoch create pocket universes with different vacuum states. Most pockets inflate eternally, but some exit inflation and enter slower expansion phases, where structures can form. Our universe would be one such pocket, a metastable vacuum that's stable enough to last billions of years, allowing stars, planets, and observers to emerge. The landscape of string theory provides a theoretical framework for this idea. String theory predicts perhaps 10 to the 500th different possible vacuum states, each with different values for the cosmological constant particle, masses, force, coupling strengths, and other parameters. Only a tiny fraction of these vacua would support complex structures. We observe a metastable vacuum with a Higgs mass of 125 GeV, not because it's special, but because vacua with significantly different Higgs masses either decay too quickly for observers to evolve or are so stable that inflation never ends. This anthropic reasoning is philosophically controversial. It abandons the goal of predicting parameters from first principles, instead accepting that they're randomly distributed across a vast landscape, and we observe typical values for observers supporting vacua. Critics argue this makes physics unfalsifiable. If any observation can be explained by "we're in the pocket universe where that value occurs," then nothing has been explained. Defenders counter that anthropic reasoning is no different from selection effects in other sciences. Just as evolutionary biology explains why we observe Earth-like environments, because that's where life, as we know it, can exist. Cosmology might explain fundamental constants through observer selection in a multiverse. The question is whether this constitutes genuine scientific explanation or a retreat from the ambition of finding unique predictive theories. Beyond vacuum instability, the metastable state creates another puzzle, the hierarchy problem. The Higgs mass is extraordinarily sensitive to quantum corrections. Virtual particles, particularly top quarks, but also W bosons, Z bosons, and Higgs bosons themselves, contribute to the effective Higgs mass through loop diagrams. When you calculate these contributions, they should be enormous, pushing the Higgs mass up to the Planck scale 10 to the 19th giga-electron-volts, unless there's some mechanism that cancels most of the corrections. The standard model has no such mechanism. The fact that the Higgs mass is only 125 GeV requires fine-tuning the bare Higgs mass, and the quantum corrections must cancel to about 34 decimal places, leaving only a small residual. This seems implausibly coincidental, like balancing a pencil on its tip, and finding it remains upright despite perturbations. Supersymmetry was proposed as a solution. In supersymmetric theories, every standard model particle has a superpartner with different spin statistics. Bosons are partnered with fermions, and vice versa. The crucial property is that supersymmetric quantum corrections have opposite signs compared to standard model corrections. If supersymmetry is exact, the corrections cancel perfectly. If supersymmetry is broken but superpartner masses aren't too far above the electroweak scale, the cancellation is approximate, keeping the Higgs mass at observable values without extreme fine-tuning. But the LHC hasn't found superpartners. Searches have excluded gluinos, superpartners of gluons, up to approximately 2.3 tera-electron-volts, squarks up to roughly 2 TeV, and neutralinos and charginos, superpartners of electroweak bosons and Higgs, up to about 1 TeV, depending on the decay mode. If supersymmetry exists, it's either broken at higher scales than theorists hoped, or it has a structure that makes superpartners difficult to detect. This negative result has led some physicists to abandon supersymmetry in favor of other solutions to the hierarchy problem. Composite Higgs models propose that the Higgs isn't a fundamental particle, but a bound state of more fundamental constituents, analogous to how pions are bound states of quarks. In these models, the Higgs mass is naturally lighter than the fundamental scale because it's a pseudo-Goldstone boson, a particle whose mass is protected by approximate symmetries. Extra-dimensional theories offer another approach. If space has additional dimensions beyond the familiar, 3-gravity might propagate through all dimensions, while standard model particles are confined to a 3-dimensional brane. This would dilute gravity's strength in our 3 dimensions, potentially bringing the Planck scale where gravity becomes as strong as other forces down to energies near the electroweak scale. The hierarchy problem would then be reframed. Instead of asking why the Higgs is so much lighter than the Planck scale, we'd ask why the extra dimensions have the particular size that brings these scales close together. LHC searches for extra dimensions look for several signatures. If extra dimensions exist, particles moving through them would appear to us as massive replicas of standard model particles' Kaluza-Klein modes. Producing these in collisions would show up as unexpected resonances at specific masses. Additionally, if gravity propagates through extra dimensions, high-energy collisions might produce microscopic black holes that would immediately evaporate through Hawking radiation, creating distinctive spray patterns of particles. None of these signatures have been observed constraining the size of potential extra dimensions. If they exist, they must be smaller than approximately 10 to the minus 19th meters beyond the LHC's resolution. Or they're configured in ways that don't produce observable signals. For instance, if standard model particles partially propagate into the extra dimensions, rather than being completely confined to a brane, the signatures would be more subtle. The absence of new physics at the LHC has created what some call the naturalness crisis in theoretical physics. For decades, naturalness, the principle that dimensionless ratios of physical quantities shouldn't be extremely large or small without explanation, guided theoretical development. Naturalness arguments predicted supersymmetry or other new physics around the TV scale. The fact that none has appeared either means naturalness is wrong as a guiding principle, or the new physics is just beyond current reach, or we haven't recognized its signatures in the data. Some physicists have begun questioning whether naturalness should be expected at all. Perhaps the Higgs mass is simply fine-tuned, and we observe this particular value because it's required for complex structures. Or perhaps there's a mechanism we haven't discovered that naturally produces small ratios without new particles at accessible energies. The CERN experiments continue refining measurements and searching for subtle deviations from standard model predictions, because even if new particles aren't directly produced, their existence might be inferred through precision, measurements of known particles' properties. Virtual effects from heavy particles contribute to processes like Higgs production and decay W boson, mass muon, magnetic moment, and flavor-changing neutral currents. Any of these could show small discrepancies pointing to new physics. And this brings us to the most intriguing cracks in the standard model, the anomalies suggesting something genuinely new might be appearing in the data. Physics recognizes 4 fundamental forces governing all interactions in the universe. Gravity shapes cosmic structure and planetary orbits. Electromagnetism governs light chemistry, electricity, and magnetism, essentially all phenomena we experience directly in daily life. The strong nuclear force binds quarks into protons and neutrons, then binds those into atomic nuclei, preventing electromagnetic repulsion from blowing nuclei apart. The weak nuclear force mediates radioactive decay, enables fusion in stellar cores, and is responsible for neutrinos interacting with matter. These forces have been tested extensively, and their predictions verified to extraordinary precision. Quantum electrodynamics, the quantum theory of electromagnetism, predicts the electron's magnetic moment to 12 decimal places, matching experimental measurements exactly. Quantum chromodynamics explains the strong force with equal precision once you account for computational difficulties in solving its equations. The electroweak theory, unifying electromagnetism and the weak force won Sheldon Glashow, Abdus Salam, and Steven Weinberg the Nobel Prize, and has been confirmed in thousands of experiments. Yet recent measurements suggest something is wrong. Not grossly wrong, but wrong at the level of precision that historically signals new physics. The most prominent anomaly involves the muon's magnetic moment. Muons are essentially heavy electrons, identical in every property except mass, which is 207 times larger than the electrons. Like electrons, muons have intrinsic angular momentum spin and act as tiny magnets. The strength of this magnetism is quantified by the magnetic moment, and quantum field theory predicts its value through summing contributions from all possible virtual particle processes. The tree-level prediction is simple. The muon's magnetic moment should equal its charge times its spin times, Planck's constant divided by twice its mass. But quantum corrections modify this through processes where virtual particles briefly appear and disappear around the muon. An electron-positron pair might momentarily form, interact with the muon, and annihilate. A photon might split into a muon-antimuon pair that quickly recombines. These virtual processes slightly enhance the magnetic moment beyond the tree-level value. Calculating these corrections requires summing thousands of Feynman diagrams representing all possible virtual processes. The calculation is extraordinarily complex, pushing the boundaries of computational particle physics. But theorists have done it, including corrections from electromagnetic interactions, weak interactions, strong interactions through virtual quarks and gluons, and even contributions from the Higgs boson. The result, published in multiple independent calculations, predicts the muon magnetic moment to better than 1 part per million. The experimental measurement comes from the Muon G2 experiment, first conducted at Brookhaven National Laboratory and recently repeated at Fermilab with improved precision. The experiment sends muons into a precisely calibrated magnetic field, where they precess their spin axes rotate around the magnetic field direction. The precession frequency depends on the magnetic moment. By measuring how fast muons precess and comparing it to the magnetic field strength measured independently using nuclear magnetic resonance, with extreme precision, experimentalists extract the magnetic moment. The result disagrees with theoretical predictions. The measured value is approximately 0.001, larger than predicted, a deviation of roughly 2 parts in 10 million. In percentage terms, that's 0.02%. For most purposes, this would be considered perfect agreement. But in particle physics, where predictions and measurements routinely match to 8 or 10 decimal places, a 0.02% discrepancy is enormous. The statistical significance is approximately 4.2 sigma, meaning there's roughly a 1 in 40,000 chance. The discrepancy is a statistical fluctuation. That's not quite the 5 sigma threshold physicists conventionally require to claim discovery, but it's close enough to take very seriously. If the discrepancy is real, it implies new physics. Something is contributing to the muon's magnetic moment that isn't in the standard model. The leading hypothesis is a new force carrier, a particle analogous to the photon, W boson, Z boson, or gluon, but coupling to muons and possibly other particles through interactions not described by existing theories. One candidate is the dark photon, a hypothetical particle that couples to dark charge carried by dark matter particles. If muons have a tiny coupling to dark photons, perhaps through quantum mixing with ordinary photons, virtual dark photons would contribute to the muon magnetic moment, just like virtual photons do, but with different strength. Depending on the dark photon's mass and coupling constant, it could produce precisely the observed discrepancy. CERN is searching for dark photons by looking for events where particles seem to appear from nothing. A dark photon produced in a collision wouldn't interact with detectors directly, but it might decay into electron-positron pairs or muon-antimuon pairs, which would be detected. The signature would be pairs of leptons with invariant mass equal to the dark photon mass appearing with rates higher than background processes predict. Another possibility is a leptoquark, a particle that couples to both quarks and leptons, potentially mediating transitions between them. The standard model keeps quarks and leptons largely separate, except through weak interactions. Leptoquarks would create new connections, allowing quarks to transform into leptons or vice versa through processes forbidden in the standard model. If leptoquarks couple more strongly to muons than to electrons, a property called lepton flavor universality violation, they could explain the magnetic moment anomaly while remaining consistent with electron measurements. LHCb experiments have found hints of lepton universality violation in B meson decays. Certain decays that can produce either electrons or muons appear to favor muons slightly more than the standard model predicts. Multiple measurements across different decay channels show similar patterns, and while each individual measurement has modest statistical significance, the combination is intriguing. The measurement that garnered the most attention involves B mesons decaying to K mesons, kaons, and lepton pairs. The standard model predicts this decay should produce electron pairs and muon pairs with nearly identical rates, differing only by a small factor accounting for the muon's larger mass. But LHCb data shows B mesons producing muon pairs at a rate about 15% lower than electron pairs, a statistically significant deviation if confirmed. Separately, the W boson mass measurement presents another anomaly. In April 2022, the CDF collaboration at Fermilab announced they'd measured the W boson mass using data collected years earlier when the Tevatron Collider was operating. Their result, 80.433 giga-electron volts, with an uncertainty of plus or minus 0.009 GeV. This precision is impressive, better than 0.01%, but it conflicts with the standard model prediction of 80.357 GeV based on measurements of other electroweak parameters. The discrepancy is 7 standard deviations, a 6 sigma result that, if correct, definitively indicates new physics. However, this measurement is controversial. Other experiments, including LEP measurements from CERN and ATLAS measurements at the LHC, found W boson masses consistent with the standard model prediction. The CDF result stands alone, creating uncertainty about whether it reflects genuine new physics or systematic experimental error that hasn't been properly accounted for. The theoretical implications, if the CDF measurement is correct, are profound. The W boson mass is precisely related to other electroweak parameters through the Higgs mechanism. If the mass is heavier than predicted, something must be modifying the relationship, either through new particles contributing to the W boson mass through quantum corrections, or through additional Higgs bosons that alter electroweak symmetry, breaking, or through modifications to the Higgs sector that change how particles acquire mass. New measurements from ATLAS and CMS at the LHC are underway to resolve this discrepancy. These experiments have larger data sets and different systematic uncertainties compared to CDF. If they confirm the higher mass, the standard model is definitively incomplete at the electroweak scale. If they support the standard model prediction, the CDF result will likely be attributed to subtle experimental systematics. Beyond these specific anomalies, physicists are pursuing theoretical frameworks that could explain multiple observations simultaneously. Supersymmetry remains a candidate despite the LHC's null results. In certain supersymmetry models, superpartner particles are heavy enough to evade detection but still contribute to precision observables through virtual effects. Fits to global electroweak data show that some supersymmetric scenarios provide better agreement with all measurements than the standard model alone, though the improvement is modest. The Higgs portal provides another theoretical avenue. If the Higgs boson couples to a dark sector containing dark matter particles and possibly additional forces, this coupling could manifest in several ways. Dark matter particles might be produced in Higgs, decays carrying away energy, and making the Higgs appear to decay to invisible final states at rates exceeding neutrino contributions. Or loop diagrams involving dark sector particles might modify the Higgs production rate or decay branching ratios in subtle ways. CERN experiments measure Higgs properties extensively to search for these effects. The Higgs production cross-section has been measured in multiple channels: gluon fusion, vector boson, fusion, associated production with W or Z bosons, associated production with top quarks, and all results agree with standard model predictions, within uncertainties of roughly 10 to 20%. Decay branching ratios to bottom quarks, tau leptons, W bosons, Z bosons, and photons have been measured with similar precision, again showing agreement. However, certain decay channels remain difficult to measure. The Higgs decay to charm quarks hasn't been definitively observed because charm jets are difficult to distinguish from bottom quark jets and light quark jets. The Higgs decay to muon pairs is just barely within reach. A few signal events on large backgrounds and measurements are consistent with standard model predictions, but with large uncertainties, and the Higgs decay to invisible final states is constrained to be less than roughly 13% of all decays, leaving room for modest dark sector coupling. The search for a fifth force also extends beyond particle physics. Astrophysical observations provide complementary constraints. If dark matter interacts through a new force mediated by light particles, this would affect dark matter's distribution in galaxies and galaxy clusters. Simulations of structure formation incorporating dark forces predict different density profiles, satellite galaxy populations, and merger rates compared to purely gravitational dark matter. Observations of the Bullet cluster and similar systems where galaxy clusters have collided show that dark matter is collisionless. It passes through itself during mergers, rather than interacting strongly. This constrains the strength of potential dark forces. If dark matter particles scattered off each other frequently, they would slow down during collisions, creating observable effects that aren't seen. The data implies that if a dark force exists, it's weaker than electromagnetism by many orders of magnitude or operates only at very short ranges. Fifth force searches also include tabletop experiments testing for deviations from Newton's inverse square law at short distances. If extra dimensions exist, or if new particles mediate forces at millimeter or micron scales, precision measurements of gravitational attraction between test masses might detect departures from predicted behavior. So far, such experiments have found nothing, but they continue to set increasingly stringent limits. The most speculative fifth force proposals involve modifying gravity itself. Some theories suggest dark energy might not be a cosmological constant, but a new field quintessence that couples to matter and creates an effective fifth force with repulsive character at cosmic scales. Other theories propose chameleon fields that have different effective masses depending on local density, making them heavy and thus short-ranged in dense environments like laboratories but light and thus long-ranged in cosmic voids. Testing these ideas requires combinations of particle physics, astrophysics, and cosmology. CERN contributes by constraining which particles can exist and how they interact. Even negative results are valuable. Every exclusion narrows the parameter space where new physics can hide. But particle physics alone can't answer the deepest questions. The tools we're building now are approaching fundamental limits imposed by energy requirements and technological capabilities. To go further requires thinking beyond current collider paradigms. The Large Hadron Collider is the most powerful machine humanity has ever built, 27 kilometers in circumference. Superconducting magnets cooled to near absolute zero. Protons accelerated to 99.999991% the speed of light. Over a decade of operation, trillions of collisions, the discovery of the Higgs boson, dozens of exotic particles, measurements of unprecedented precision, and scientists are already designing its replacement, not because the LHC failed, because it succeeded. It answered questions and raised new ones. It found the Higgs and revealed the instability of the vacuum. It confirmed the standard model and exposed its limitations. It pushed to the edge of current technology and showed us what lies just beyond. But to go further, to probe higher energies and rarer processes, we need more. More collisions, more data, more power. The first step is the high luminosity LHC, an upgrade scheduled to come online in the late 2020s. It won't increase the collision energy, but it will increase the collision rate by a factor of 10. More beams, tighter focus, more protons smashing together per second. The result, 10 times as many collisions, 10 times as much data, 10 times more chances to catch rare events. Think of it like buying lottery tickets. If you have one ticket, your odds of winning are minuscule. If you have 10 tickets, your odds are 10 times better. The high luminosity LHC is buying more tickets. It's not changing the game, but it's increasing the chances of hitting the jackpot, finding that one anomalous event, that one signature of new physics buried in the noise. But the real future lies in a new machine, the Future Circular Collider, the FCC. This is the next generation design, and it's audacious. a tunnel 100 kilometers in circumference, nearly 4 times the size of the LHC. It would circle under Lake Geneva beneath the Jura Mountains, cutting through the countryside of France and Switzerland in a vast loop. If you stood at one point on the ring and looked straight ahead, the curve would be so gentle you couldn't see it for tens of kilometers. The FCC would collide particles at energies 7 times higher than the LHC, 100 tera-electron volts. That's 100 trillion electron volts, enough to recreate conditions even closer to the Big Bang, to probe energy scales where new forces might unify, where supersymmetric particles might appear, where the fabric of space-time itself might reveal deeper structures. The cost, 20 billion euros, maybe more. Construction would take decades. If they started today, it wouldn't be operational until the 2050s. The people designing it now, the scientists planning the experiments, most of them won't live to see it completed. They're building it for the next generation. For physicists who are children today or not yet born, this is science as a relay race. Each generation hands the baton to the next. Newton to Einstein, Einstein to Bohr and Heisenberg, Feynman and Gell-Mann to the builders of the first particle accelerators, the discoverers of quarks to the designers of the LHC, and now the LHC generation to the FCC generation. The questions evolve. The tools become more sophisticated. The answers lead to deeper questions. But the search continues unbroken across centuries. And CERN isn't the only player. China is designing the Circular Electron-Positron Collider, the CEPC, also 100 kilometers in circumference, but focused on studying the Higgs boson with extreme precision rather than chasing maximum energy. It could be operational by the 2030s, a decade before the FCC. This creates a friendly but fierce competition. Who will make the next breakthrough? Who will find the fifth force, the dark matter particle, the crack that opens up a new era of physics? The race is global, the stakes are enormous, and the prize is understanding. But there's a darker question lurking beneath the ambition. What if we build these machines, spend the billions, dedicate the decades, and find nothing? What if the anomalies disappear with more data? What if the Muon G-2 measurement turns out to be a statistical fluctuation? What if supersymmetry doesn't exist? Extra dimensions are too small to detect, and the Higgs portal leads nowhere. What if the universe is simpler than we hoped? What if the standard model, for all its gaps, is as good as it gets at the energies we can reach? What if dark matter and dark energy operate on scales so far removed from particle physics that no collider, no matter how powerful, can touch them? This is the fear that haunts physicists. Not that they'll fail to find answers, but that there are no answers to be found. That the universe is structured in such a way that the next layer of truth is beyond our reach, separated by an energy gap we can never cross. But even if that's true, even if the FCC finds nothing beyond what the LHC already discovered, the search itself has value, because we learn from null results. We learn what the universe is not, which narrows down what it could be. We refine our theories, eliminate possibilities, sharpen our questions. Every experiment, successful or not, adds to the body of knowledge. Every measurement, even if it confirms the standard model, again tightens the constraints, makes the theory more robust. And, more importantly, the search represents something fundamental about humanity. We are the species that asks why. We build cathedrals to curiosity. We spend fortunes not on weapons or conquest, but on understanding. We cross borders, collaborate across languages and cultures, and pool our resources to answer questions that have no practical application. Why does the universe exist? What is it made of? Where did we come from? Where are we going? These questions don't put food on the table. They don't cure diseases or power cities, but they define us. They're what separate us from every other species on the planet. We don't just survive. We wonder, we question, we search. And that search never ends. Every answer is a stepping stone to the next question. Every discovery reveals new mysteries. The more we learn, the more we realize how much we don't know. This is not a failure, it's the point. Because if we ever reached the end, if we ever answered every question and had nothing left to discover then what would drive us? What would inspire the next generation? The beauty of science is that it's infinite. The universe is vast, complex, layered with mysteries at every scale. From the quantum foam of space-time to the cosmic web of galaxies. From the first moments of the Big Bang to the heat death, trillions of years in the future, there's always more to explore. Always another door to open. And the tools we build, the colliders and telescopes and detectors, are keys. Some doors they open easily. Some remain locked, waiting for better keys, more refined tools, new ideas. But we keep building. We keep searching. We hand the keys to the next generation and say, "Here, we got this far, now you go further." That's the legacy of CERN. Not just the discoveries, but the persistence. The refusal to accept ignorance as final. The commitment to pushing the boundaries of knowledge, even when the answers are elusive, even when the questions seem impossible. And maybe, just maybe, the cracks they're finding, the anomalies, the imbalances, the particles that shouldn't exist, will be the keys that unlock the next great revolution in physics. A theory that explains dark matter and dark energy. A framework that unifies all the forces. An understanding of why the universe exists and why it's structured the way it is. Or maybe not. Maybe the answers lie beyond our reach, in energy scales or conceptual frameworks we can't yet imagine. But the search continues anyway, because searching is what we do. It's who we are. And that brings us back to the question we started with. Why are they hunting for cracks? Why dedicate so much effort, so many resources, to finding where physics breaks? Because cracks are not weaknesses, they're invitations, and the universe is inviting us to look deeper. 27 kilometers underground, particles colliding 600 million times per second. Scientists from 100 countries staring at data, searching for deviations, hunting for cracks in the most successful theory physics has ever produced. This is where we started. And now, after traveling through the Big Bang, through dark matter and antimatter, through vacuum decay and quantum entanglement, through the fifth force and the machines of tomorrow, we can finally understand what those cracks really mean. They're not failures. They're not signs that we got something wrong. They're doors, openings through which light enters. Every great revolution in physics started with a crack, with something that didn't fit a measurement that defied explanation, an observation that shattered the prevailing theory. Newton's laws worked perfectly for centuries. They described the motion of planets, the trajectories of cannonballs, the swing of pendulums. Then scientists measured the orbit of Mercury and found it precessed slightly more than Newton predicted. A tiny anomaly, a crack. And through that crack, Einstein saw general relativity, the curvature of space-time, gravity not as a force, but as geometry. Classical physics said light was a wave. Then experiments showed it came in discrete packets, photons, a crack. Through it came quantum mechanics, the realization that reality at the smallest scales is probabilistic, uncertain, fundamentally weird. The Standard Model predicts particle masses with incredible precision. Then the muon's magnetic moment measures too high, another crack. Through it, maybe we'll glimpse the fifth force, or supersymmetry, or something no one has imagined yet. Cracks are where progress happens, where ignorance transforms into curiosity, where the comfortable certainty of "we know this" gives way to the electric possibility of "what if?" And CERN is built on that possibility, on the idea that the universe is stranger than we think, that the 5% we understand is just the beginning, that the 95% we don't see is out there waiting, structured by forces and particles we haven't discovered yet. This is the real gift of the cracks. Not the specific discoveries, though those matter, but the reminder that we don't know everything. That reality is deeper, richer, more complex than our current theories suggest. That there's always more to find. And that brings us to the deepest mystery of all. The one CERN can't solve, but points toward anyway. In 13.8 billion years of cosmic history, the universe was mostly silent. Stars burned, galaxies collided, black holes devoured matter. But none of it asked why. None of it looked at itself and wondered about its own existence. Then, on at least one small planet orbiting an ordinary star, in an unremarkable galaxy, something extraordinary happened. The universe became conscious. Matter arranged itself into patterns, complex enough to reflect, to question, to understand. You are made of stardust. This is not poetry, it's physics. Every atom in your body, heavier than hydrogen, was forged in the core of a dying star, blasted into space by a supernova, eventually coalescing into the planet you stand on. The calcium in your bones, the iron in your blood, the carbon in your DNA, all of it was created in stellar furnaces billions of years ago. But more than that, you are the universe looking at itself. When you gaze at the stars, it's the cosmos recognizing its own structure. When you ask where you came from, it's reality questioning its own origins. You are not separate from the universe. You are a process, it's running. A pattern, it's exploring. And here's the staggering part. Through science, through telescopes and colliders and mathematics, the universe has figured out where it came from. It has traced its own history back to the Big Bang. It has discovered its own composition, mapped its own structure. Matter has become aware of matter. Energy has learned to calculate energy. This is the crack CERN can't explain. Consciousness, awareness, the fact that the universe contains entities capable of understanding it. Physics can describe every particle, every force, every interaction. It can calculate the mass of the Higgs boson, predict the decay of a muon trace, the evolution of galaxies, but it can't explain why any of that gives rise to subjective experience, to the feeling of being, to the sense that you are here now, aware of your own existence. This is the hard problem of consciousness. And it might be the ultimate crack, the place where physics, for all its success, reaches a boundary, where the equations, no matter how precise, can't capture the full reality of what it means to exist. But maybe that's okay. Maybe not everything needs to be reduced to particles and forces. Maybe consciousness is a different kind of phenomenon, emergent from complexity in ways we don't yet understand. Or maybe it's fundamental, woven into the fabric of reality at a level deeper than quantum fields. We don't know. CERN can't tell us. But the fact that we're asking, the fact that we're aware enough to wonder about our own awareness is itself remarkable. And it connects back to the cracks. Because consciousness is what drives the search. Particles don't care about dark matter. Stars don't wonder about the stability of the vacuum. Only conscious beings ask these questions. Only we build machines to probe the unknown. The search for cracks is ultimately the search for ourselves, for our place in the cosmos, for the meaning of existence in a universe that doesn't seem to need meaning. And what we found is that we're tiny, unimaginably small, a speck on a speck in a galaxy that's one of trillions, made of particles that are themselves mostly empty space, held together by forces we barely understand, existing in a universe that's 95% invisible. But we're also magnificent. We're the part of the universe that woke up, that learned to ask questions and build tools to answer them, that looked at the night sky and didn't just see lights, but saw a history stretching back billions of years. That took rocks and lightning and turned them into computers. That built a 27-kilometer tunnel underground just to satisfy curiosity. We are fragile and temporary. Our planet will eventually be consumed by the sun. Our galaxy will collide with Andromeda. The universe will expand until every star burns out and every black hole evaporates. On cosmic timescales, we're a brief flicker, here and gone. But right now, in this moment, we're here, aware, searching, wondering. And the cracks we find, the mysteries we uncover, they're gifts. Invitations to keep exploring, keep questioning, keep pushing against the boundaries of knowledge. Because as long as there are cracks, there are reasons to search. And as long as we search, we're alive in the deepest sense, engaged with reality, participating in the universe's ongoing process of self-discovery. CERN will keep running. The LHC will be upgraded, the FCC will be built, or something like it. Scientists will collide particles at ever higher energies, measure anomalies with ever greater precision, hunt for dark matter and fifth forces and quantum gravity. And they'll find things, new particles, new phenomena, new cracks in the standard model. Each one will answer old questions and raise new ones. The search will continue, generation after generation, with no end in sight. Because the universe is infinite in complexity. There's always another layer, another scale, another perspective. From quarks to superclusters, from quantum foam to cosmic horizons, the territory is vast and mostly unexplored. And we're only just beginning. So when you hear about CERN hunting for cracks, remember, they're not looking for problems. They're looking for doors, for windows into deeper truths, for the places where reality reveals itself to be stranger, richer, more beautiful than we imagined. And every crack they find is a gift, a reminder that we don't have all the answers, that the universe is full of mysteries, that there's always more to discover. The cracks are not where knowledge breaks, they're where wonder begins. And wonder, more than anything, is what keeps us searching, what makes us human, what connects us to the cosmos. Right now, particles are streaming through your body from distant stars. The vacuum around you is seething with quantum fluctuations. Galaxies are receding into darkness, carried by dark energy we don't understand. The universe is expanding, evolving, transforming. And you're here, a temporary pattern of matter and energy, aware of all this. Part of the 5% trying to understand the 100%, a crack in the universe's own ignorance about itself. That's not a small thing. That's everything. The hunt for cracks continues. The questions multiply. The mysteries deepen. And that's exactly as it should be. Because a universe with nothing left to discover would be a universe without wonder. And without wonder, we're just particles in motion. With wonder, we're something more. We're the universe awake and asking why.